right, so the clock is almost working now. It's an hour behind, but at least it's the minute hand and the second hand are working, and it tells us it's time to start. So today, well, first off, the quizzes have been graded and returned to the boxes. So if you were not in the class last semester, the return boxes for our quizzes and exams is just down the hall on the left as you're heading towards the department office. There's a display case with my name in it, and that will have the answer keys to the quizzes and exams. And then the alphabetical slots below that are where you can pick them up. So on Wednesday, we introduced the topic of electrophilic aromatic substitution. And these are our 5 electrophilic aromatic substitution reactions we're learning in this chapter. We learned the common mechanism. Today we're going to go through those reactions. And the last 2 steps of each mechanism will be identical. What will be different in each case is how we form the electrophile. Okay? So we're going to start with halogenation. We've had halogenations of alkenes. That's something we've seen before. Now we're doing halogenation of benzene, but it's not an addition reaction, it's a substitution reaction. It only works with bromine and chlorine. This is one of those reactions where fluorine is too reactive and iodine is not reactive enough. And we need a catalyst. The iron trihalide, so either tribromide or trichloride, is required in this reaction. It can be generated from iron metal and either bromine or chlorine. So sometimes you can just add iron itself and react it with excess of the halogen to form it in situ. But regardless of how you make it, we're just going to write iron tribromide or iron trichloride when we are drawing the mechanism. So what is the electrophile in halogenation and how do we form it? So we're going to draw it with bromine, but it'll be the same if we were drawing it with chlorine. Bromine or chlorine are Lewis bases. They have plenty of lone pairs on them. And iron salts, like many of our metal salts, are good Lewis acids because they have metal ions with partial positive charges that have empty orbitals. And so we start out with just a lone pair on the bromine attacking the Lewis acid. And that's going to give us a Lewis acid, Lewis base complex, which will look like this. We're going to have formal charges on the iron and the bromine. These charges, because they're formal charges, they're not full +1 and -1 charges. They're partial charges, but this bromine does have a partial positive charge on it. So this Lewis acid, Lewis base complex is electrophilic. So when it encounters a benzene molecule, the pi electrons from benzene can function as a nucleophile and can attack this. So we can just write E+ below here because this is our electrophile in our Friedel-Crafts reaction. But our benzene ring is not going to attack our positively charged bromine. It's actually going to attack the other bromine. And I'll show you why. If the pi electrons attack the bromine on the end, we can cleave the weak bromine-bromine bond. And by converting this pair of electrons from a bond pair to a lone pair, we're going to get rid of that formal positive charge on the bromine. So that's why we're attacking the bromine adjacent to the one that is positively charged. Okay? So that gives us FeBr4, which is an anionic species, as a byproduct. We'll see that play another role in the reaction in a moment. And then we're going to have a cyclohexadienyl cation, where we have a bromine now attached to what was benzene. So this cation is not aromatic. This is our rate determining step because we're losing aromaticity. But it is a resonance stabilized cation. So as far as cations go, it is reasonably stable because we have two additional resonance structures that we can draw. Now, you don't have to draw, unless you're specifically directed to, you do not have to draw all of the resonance structures of this cation when you're drawing mechanisms of electrophilic aromatic substitution. You can draw just one of them, and that will usually suffice. Okay, but today I'm going to draw all three for you, just so that you see what they look like, and remember that this is a resonance stabilized cation with the positive charge shared by 3 carbons in the ring. Okay. Now, when we have a resonance stabilized intermediate in a reaction, we can draw the mechanism using any of those resonance structures. So you could draw this mechanism using any of these 3 resonance structures. The only thing that would differ is how many curved arrows you use and where you draw the curved arrows. So it doesn't really matter which of these resonance structures you draw when you're drawing the mechanism. So for the last step, I'm going to use this one just because it's on the end, but it doesn't really matter which one I would use. So this cation is basically crying out for a base to come and deprotonate it so that you can reform the aromatic ring and it can gain that stability from aromaticity, can get back to being aromatic. So in general, carbocations are highly acidic. You don't need a very strong base to deprotonate a carbocation to do an elimination to form an alkene. And that's especially true when it's a cyclohexadienyl carbocation, because if you deprotonate that, you end up with an aromatic ring. So the iron tribromide that we formed as a byproduct in this step over here can act as a base. Notice we've drawn the formal negative charge on the iron. Because bromine is much more electronegative than iron, the negative charge really resides on these bromine atoms. Okay, so this is one of those quirks of Lewis structures where you put the negative charge on the iron, but it's really on the bromines, right? And this is another reminder: the negative charge does not equal lone pair. There's no lone pair associated with that negative charge. So what we use as the base is electrons in an iron bromine sigma bond. So we use those electrons in the iron bromine sigma bond to deprotonate this hydrogen. We use the electrons in the carbon hydrogen sigma bond to form the pi bond, and that gives us our bromobenzene product. Okay, and then you'll see that we're forming HBr. We form one equivalent of HBr in this reaction as a byproduct. And then we're also forming iron tribromide. Since we use that in the first step, iron tribromide is a catalyst in this reaction. It's regenerated, and so you could use it in substoichiometric amounts in this reaction. Okay? Any questions about our halogenation mechanism? Yes, please. Yes. So why does this happen? So that's a great question. It happens because we've generated another sigma bond, right? And bonding is a favorable process. And so that outweighs the fact that we've generated formal charges. And then just recognize that these formal charges aren't as bad as they look. Yes, they would add a little bit of energy, decrease the stability, but because they're only formal charges, they're really small. They're not that big. And so any kind of instability due to those formal charges is outweighed by the fact that we've generated another sigma bond. Okay, good question. Other questions? Yes. Yes. Those are the most common ones. So borohydride was one that we showed you last semester that we're going to show you again this semester. Yeah, so usually when you have a metal or a metalloid and you have more electronegative atoms attached to it, that's the most common case where you get this scenario where a negative charge does not equal a lone pair. Okay, so the mechanism would be identical with chlorine. We would just be using Cl2 and FeCl3. Okay, question, Grace? Generally, you don't, because sometimes you're making it in situ by just adding iron, and so obviously you wouldn't ever have the cross in that case. I'm not certain, but it might be possible to reverse the process and generate some of the other halogen, in which you might get scrambling. So I don't know if it's possible or not, but I think both FeCl3 and FeBr3 are widely available. So typically you would use the one that, it would be easy for you to use the one that corresponds to the halogen that you were attaching. Good question. So alkylbenzene, halobenzenes are very common. They're common in pharmaceuticals. They're common in molecules used for other purposes. Here we have an aid that's used to help people quit smoking. Here we have a common antihistamine. We talked about histamine on Wednesday. This is one of the compounds you can take to block the effects of histamine. And then Agent Orange, you guys are too young to know much about the Vietnam War probably, but the Vietnamese soldiers were hiding in the jungles of Vietnam. And so the US military dropped Agent Orange on the jungle because this is an herbicide. It kills plants. So when they dropped it on the jungle, it killed the plants in the jungle. So there were less places for the opposing soldiers to hide. Okay, so chlorobenzenes or halobenzenes can be used for a lot of purposes. One of my favorite ones is vancomycin. If you look back at the structure of vancomycin, which we talked about last semester in class, the antibiotic of last resort, you'll see that it has chlorines attached to the benzene ring. So there's lots of reasons to perform brominations and chlorinations to attach these atoms to benzene rings. So our next reaction is the nitration reaction. And the nitro group, the NO2 group, is not as commonly found. Sorry, I'm raising the wrong board. Not as commonly found in pharmaceuticals or other organic molecules that are used for commercial purposes. But it is converted to the amino group, which is very common in pharmaceuticals and other species. So if we take benzene, we can react benzene with nitric acid and sulfuric acid. So we use two strong acids in this reaction. Okay, so we get a nitro group on the benzene ring. This is called nitrobenzene. And then we can reduce the nitro group. There are a few different ways to do this, but hydrogen and palladium carbon is probably the most common. It's a very simple way of reducing the nitro group to an amino group. So this is aniline. This is a way you could make aniline. And then there are many other substituted benzenes that have an NH2 group. You can't put this group on directly to benzene, and so we do it indirectly by generating a nitro group first and then reducing it. This is a reaction sequence we've done many times in the past in my lab as well when we needed these amino groups on benzene rings. Okay, so let's look at the mechanism on the screen because it has similarities to the mechanisms we've already drawn on the board for you. And I should also mention that typically the Chem 354 curriculum has a nitration reaction in it. They've usually nitrated ferrocene. I'm not sure if you'll get to do that this year because things are being adjusted, but many times you get to run this reaction in the lab yourself. Okay, so it may seem unusual to have one acid protonate another acid. These are both strong acids. Sulfuric acid is stronger than nitric acid, Nitric acid is kind of on the border between strong and weak acids. But nitric acid, because it has oxygens with lone pairs, it is also basic as well, in addition to being an acid. And if you treat it with a strong enough acid, such as sulfuric acid, you can protonate the OH oxygen. And when you do so, you have the elements of water. And we've seen oxonium ions cleave to lose water. We've seen that before as a way of forming carbocations. In this case, because it's attached to a nitrogen, we're not forming a carbocation, we're forming a nitronium ion. And this is what a nitronium ion looks like. It looks like CO2, but it has a nitrogen in the center instead of a carbon. And because nitrogen has owns one more valence electron than carbon, when it has these 4 bonds, it now has a positive charge on it. So this is quite electrophilic. We'll take a look at the rest of the mechanism on this page. So here they've shown you a little bit of forming the electrophile. I wish they would draw out the resonance structure like they did on the other slide, but you can draw that out too, the Lewis structure, I should say. And so our benzene ring attacks that central nitrogen that's positively charged, and then we get our resonance stabilized cation. I wish they would draw this out. This is one of the only places in the book where they've broken the cardinal rule of pretending that a negative charge is a lone pair. It's not. You would draw out HSO4 minus. I usually draw it out like this, right? So it's one of the lone pairs on this oxygen that is deprotonating that cation and generating the product, okay? Any questions about the nitration mechanism? Okay. So our next reaction is comparable. So again, just one thing to reiterate, it's the conjugate base of our sulfuric acid, which is functioning as an acid in the first step, that is functioning as our base. So we are regenerating sulfuric acid in this reaction. A very similar reaction is the sulfonation reaction. So we take benzene, we react it with sulfur trioxide. In this reaction, we also use sulfuric acid. I'm going to draw out the sulfonic acid group. The book just shows it as SO3H. This is what it actually looks like if you're drawing out the Lewis structure. Okay. It looks a bit like sulfuric acid with a benzene ring attached as opposed to one of the OH groups of sulfuric acid. And so like sulfuric acid, it is a strong acid. Last semester, we learned about toluene sulfonic acid, or TSOH. If we had a methyl group here, then that would be toluene sulfonic acid. This is actually benzene sulfonic acid, closely related to toluene sulfonic acid. Both of these are strong acids that are soluble in organic solvents. And so that's why sulfonic acids in general are useful, organic soluble strong acids. And the way you make them is by reacting benzene or substituted benzenes with sulfur trioxide in sulfuric acid. So what is the electrophile in this case, and how do we form it? It's sulfur trioxide, which looks like this. You'll notice we've broken the octet, but we can do that because sulfur is a third row element and has d orbitals. This is a neutral molecule because sulfur is in the 6th column of the periodic table. And if we count our valence electrons here, it owns 6 electrons, right? So this is a neutral sulfur. If we react sulfur trioxide with sulfuric acid, we can use electrons in one of our sulfur oxygen double bonds to pick up a proton. Then we have a species looking like this. Now our sulfur only owns 5 electrons. Even though it's got access to 10, it's still exceeding the octet. It only owns 5 of those electrons. And so indeed, this is positively charged on the sulfur and is therefore now an electrophile. And of course, we've also formed HSO4 minus. So what's going to happen next? We're not going to draw this out. You should draw this out on your own just to familiarize yourself with it. But our benzene is going to attack on the sulfur. And then our HSO4 minus is going to deprotonate the resulting resonance stabilized cation to give us our benzene sulfonic acid, which we see right here. Okay. Any questions on sulfidation, on how we form the electrophile, or on what comes next in the mechanism? Okay, let's go on to the Friedel-Crafts reactions. These were named for the 2 chemists who discovered and researched these reactions. The Friedel-Crafts alkylation attaches an alkyl group to our benzene ring. And we typically use an alkyl chloride as the reagent in this case. Actually, I'll put it over the arrow. And then we use aluminum trichloride as a Lewis acid. Generally speaking, aluminum Lewis acids are stronger Lewis acids than iron Lewis acids. And the Friedel-Crafts reaction is usually not as fast or facile as halogenation. So we need a stronger Lewis acid, an aluminum Lewis acid in this case. So we use alkyl chlorides, aluminum trichloride. This allows us to attach an alkyl group to our benzene ring. We're going to form HCl as a byproduct in this reaction. So you'll notice that in a Friedel-Crafts alkylation, we are forming a carbon-carbon bond. And last semester, we learned that carbon-carbon bond forming reactions are special because they allow us to take smaller organic molecules, join them together to make larger organic products. And so the Friedel-Crafts alkylation is another way to form carbon-carbon bonds. So this is a special reaction, as is the related Friedel-Crafts acylation. Okay. So in a Friedel-Crafts acylation, instead of using an alkyl chloride, we use a molecule called an acid chloride. Okay. Now, you might be asking, where's the acid? This molecule itself is not an acid. It is derived from an acid. You make an acid chloride by starting with a carboxylic acid. That's something we're going to learn in a few chapters. Okay. So an acid chloride is named because it is derived from an acid, not because it is an acid itself. So don't waste any time looking for acidic hydrogens in acid chlorides. Okay. So the acid chloride reacts with benzene. Again, we need aluminum trichloride. And in this case, instead of attaching an alkyl group to our benzene ring, we are attaching an acyl group to our benzene ring. Okay? So we're forming a ketone. Our product is a ketone. And when you look at just half of the ketone, the part that we're attaching to the benzene ring, we refer to that as an acyl group, the part I've put in the box. Okay? So because we're attaching an acyl group to our benzene ring to form a ketone, this reaction is known as an acylation. And then, of course, HCl, once again, is formed as a byproduct. Okay? So, how do we form the electrophiles? Let's start with the Friedel-Crafts alkylation. And the nature of the electrophile depends on what kind of alkyl halide we have. If it's a primary alkyl halide, let's use chloroethane as our example. The first step of the process is going to remind us of the first step in the halogenation reaction. Our alkyl halide is Lewis basic. It has lone pairs on chlorine. Our aluminum trichloride is Lewis acidic. So lone pairs on chlorine can attack the aluminum. We're making a species that has formal charges, but we have formed a new sigma bond, so this is favorable. Okay. But this is electrophilic now. We have that formal positive charge on the chlorine. And our benzene ring can attack the carbon attached to the chlorine the same way that up here on this board on the top, our benzene ring attacked the bromine that was attached to the positively charged atom. So this Lewis acid Lewis base complex will react directly with benzene. Benzene will attack at this carbon, cleaving our carbon-chlorine bond and making AlCl4-. Okay, that's what happens when we have a primary alkyl halide reacting with aluminum trichloride. When it is a secondary or tertiary alkyl halide, the nature of the electrophile is different. Let's use tert-butyl chloride as an example. Okay, here's tert-butyl chloride. First step is going to be the same, generating our Lewis acid Lewis base complex. But now, because we have a tertiary alkyl group attached to a positively charged chlorine, we can just cleave this bond directly in a heterolytic fashion to form a tertiary carbocation and aluminum tetrachloride. Okay? So this process can occur when it is either a secondary or a tertiary alkyl group attached to the chlorine, because secondary and tertiary carbocations are stable enough to be generated. And then the carbocation will react directly with the benzene ring in the Friedel-Crafts reaction. But if it's a primary alkyl halide, the primary carbocation would be too high in energy to form. So instead, the Lewis acid Lewis base complex is directly attacked in the same way that the Lewis acid Lewis base complex is attacked in the halogenation reaction. So yeah, Brady. So if we had the possibility to have an allylic carbocation, would that also follow the Yes. If you had an allylic alkyl group, then that would form the resonance stabilized allylic carbocation, because that's usually as stable as a secondary carbocation, if not more stable. Good question. So here we have a diagram on the board of what happens once we generate our tertiary carbocation. So the benzene ring will attack the positively charged carbon, giving us our resonance stabilized cyclohexadienyl cation. You don't have to draw the extra resonance structures, but you should be able to. And then we're using the, just like we did with FeBr4-, with AlCl4-, we're using the aluminum chlorine sigma electrons as our base to deprotonate that cation, generating our tert-butyl benzene product, regenerating AlCl3 and forming our HCl byproduct. Okay. This is not a very strong base, but you don't need a strong base to deprotonate this cation. That cation is desperate to become aromatic again because it can attain the stability due to aromaticity. And so anything that's any kind of a base whatsoever will be able to deprotonate this and generate that aromatic product. Any questions? Yes. What was that? Inversion. So we don't, because so if you're wondering, if we have a chiral alkyl halide what would happen to the stereochemistry of that alkyl halide? Is that what you're wondering? Yeah, so if the carbon bearing the chlorine is a stereocenter, then that stereocenter gets destroyed when you make the carbocation. And so then when the benzene attacks and you reform it, it would be racemic. Okay, so you would have racemization. That's a great question. You would always have racemization in a Friedel-Crafts reaction. Okay, so the way we generate the electrophile in the Friedel-Crafts acylation is similar, not identical, but it is similar. So let's look at it here on the screen. The Lewis basic lone pairs on the chlorine can attack the Lewis acidic aluminum, generating a Lewis acid Lewis base complex, similar to the ones we've seen before. And here we can generate the carbocation because the cation that's formed is known as an acylium ion. It is a resonance stabilized cation. We have a lone pair adjacent to a positive charge, so we have the ability to draw a resonance structure. Of these two resonance structures, which one is more stable or the major contributor? The one on the left or the one on the right? The one on the right, exactly. Why? Yeah, the octet. All of the atoms have satisfied octets in the one on the right, whereas on the left, the carbon does not have the octet. Okay? So, although you can draw the mechanism through either of those two resonance structures, and the mechanism would be valid, the preferred way to draw the mechanism is using the major contributor, because that gives you a better picture of what that cationic intermediate looks like. The cationic intermediate looks more like this structure than it does that structure, meaning that the bond between carbon and oxygen is closer to a triple bond than a double bond, and there's more positive charge on the oxygen than there is on the carbon. So let's draw the mechanism of the Friedel-Crafts acylation, just showing that more stable major contributor. Okay? So the first step is going to be the same as what you see on the screen. I'm using our simplest acid chloride, the one derived from acetic acid. This is known as acetyl chloride. Okay. All right. So once we're at the Lewis acid Lewis base complex, we can do the same thing, cleaving the carbon chlorine bond to generate our acylium ion. But if we draw just one more curved arrow at this stage, that gets us directly to the major contributor of our acylium ion intermediate. Okay? So when I draw it, I like to draw that extra arrow because it gets me directly to that major contributor. We formed AlCl4 minus. Then our benzene reacts. Our benzene pi electrons, they're not going to, in the pattern we've seen before, they're not going to attack the oxygen, the positively charged oxygen. They'll attack the carbon adjacent to the positively charged oxygen. Of course, this carbon bears a partial positive charge, and we can see that with the resonance here. And then we would push the pi electrons up onto the oxygen, and that gives us this intermediate. Okay. Here's our resonance stabilized cyclohexadienyl cation. We could draw the other two resonance structures, but in the interest of time and space, we're just going to draw our AlCl4 minus, and we'll just draw it out like this. Whoops. Giving us our ketone product, where we've attached our acyl group. We've generated HCl, and we've generated aluminum trichloride. So if you draw the curved arrows in this fashion, you end up with our major contributor directly, and then we attack that carbon, push the electrons back to the oxygen to get our intermediate. Questions? Yes, so both the carbon and the oxygen have partial positive charges, and the oxygen has more partial charge. But by attacking the carbon, you have a product that has a carbonyl group in it, right? You get a neutral species here. If you were to attack that oxygen and push electrons onto the carbon, right, you'd end up with a weird species that would have a positive charge on oxygen and a negative charge on carbon. So you get a more stable product if you're attacking adjacent to the cation and you're pushing pi electrons onto the positively charged atom. Okay, good question. Other questions? Okay, so let's learn some facts about Friedel-Crafts alkylations. We'll start with the alkylation reaction. So we're going to erase this mechanism we just drew. We're going to talk about Friedel-Crafts alkylations. Okay, so our first fact is that vinyl chlorides and aryl chlorides are unreactive. Okay? They will not participate in these reactions. Okay? If you'll remember from 351M, we learned that vinyl chlorides and aryl chlorides, or halides in general, did not react in SN1 or SN2 reactions. You cannot form carbocations. The carbocations you would form from these molecules would be too unstable. Okay? So these are unreactive. It has to be, in a Friedel-Crafts alkylation, it has to be an alkyl halide or an alkyl group. Okay? Now, in most cases, unless it's a primary alkyl halide, we're forming a carbocation as our electrophile in a Friedel-Crafts alkylation. What can happen in reactions involving carbocations? Rearrangements, exactly. So, the second point we need to know about Friedel-Crafts alkylations is that rearrangements can occur. Okay? We can have rearrangements from primary alkyl groups to secondary alkyl groups. That's without forming a primary carbocation. I'll show you how that can happen in a moment. And then when we form secondary carbocations, if it's possible for those secondary carbocations to rearrange to generate tertiary carbocations, that can happen. So many times, if we're using a primary alkyl halide in a Friedel-Crafts alkylation, we end up with a secondary alkyl group attached to our benzene ring because of the rearrangement. If we're using a secondary alkyl halide, we're oftentimes ending up with a tertiary alkyl group attached to our benzene ring. So how does this happen? We have a mechanism for rearrangement shown here. This is using a secondary alkyl halide. So we generate our Lewis acid-Lewis base complex. We cleave our carbon-chlorine bond. Now we have our secondary carbocation. And anytime we generate a carbocation, we have to ask ourselves, is there a group on one of the neighboring carbons or the beta carbons that we could shift over one carbon to the positively charged carbon, thereby generating a more stable carbocation? If the answer to that question is yes, then that process will indeed happen because it is an intramolecular process. It does not require two molecules to collide in solution. Our carbocation does not have to collide with anything in order to undergo this 1-2 shift. And so that 1-2 shift is going to be faster than anything else that could happen to that carbocation. Faster than it could be attacked directly by benzene. That hydride shifts over, we get a tertiary carbocation. Now that we have the tertiary carbocation, that gets attacked by our benzene, giving us our cyclohexadienyl cation. Our aluminum tetrachloride deprotonates, giving us the product. Okay? Any questions on Friedel-Crafts mechanisms with rearrangement? Yes? No. That's a good point. It always has to be adjacent. Okay? So you only have to look at the beta carbons, the carbons that are directly attached to the positively charged carbon. So it's only going to happen from one atom away. Okay? Other questions? So if we use a primary alkyl group, primary alkyl chloride, and we don't form a primary carbocation, how do we have a rearrangement? We'll show you. So here we have 1-chloropropane. We're going to react that with aluminum trichloride, generating our Lewis acid, Lewis base complex. Okay. So this cannot cleave the carbon-chlorine bond to make the primary carbocation. That's too high in energy. However, it does have beta hydrogens. And we can have a 1-2 shift of a beta hydrogen concerted with cleavage of the carbon-chlorine bond. So we can have this hydride migrate at the same time as we cleave our carbon-chlorine bond. And that allows us to go directly to a secondary carbocation. The positive charge will be on this carbon. Okay. And then we have our AlCl4 byproduct. Okay. So by having the hydride shift occur simultaneous to carbon-chlorine bond cleavage, we directly form a secondary carbocation because we're rearranging at the same time as we're forming our carbocation. Okay. So once we get to this point, benzene will attack the positively charged carbon, thereby attaching an isopropyl group to our benzene ring. Okay, here's our resonance stabilized cyclohexadienyl cation. And then our AlCl4 deprotonates, giving us our isopropyl benzene. Our HCl, and regenerating our aluminum trichloride. Okay? So this can happen with any primary alkyl group that is propyl or longer. Of course, if you have chloromethane, there's no beta carbon, no beta hydrogen. So it can't happen with chloromethane, and that's just going to react. The Lewis acid Lewis base complex would react directly with the benzene in that case. If it's chloroethane, the rearrangement would just give you another primary carbocation. That's not going to happen with chloroethane. But any primary alkyl halide longer than chloroethane, which would be propane or longer, would undergo this rearrangement. Okay? So in many cases, you'll have rearrangements. You won't have them with tertiary carbocations or tertiary alkyl halides. You'll have them sometimes with secondary alkyl halides if they can rearrange to form a tertiary carbocation. And then with primary, 3 carbons or longer, you'll see these rearrangements and you'll get a secondary carbocation. Any questions? Okay, let's get out our iClickers. We have an iClicker question. What alkyl halide or halides could be used to make sec-butylbenzene in a Friedel-Crafts alkylation reaction? So first you have to know what sec-butylbenzene is. If you don't, talk to your neighbor, and hopefully your neighbor knows what a sec-butyl group is. And then you can draw these structures out if you don't know what they are, just based on the names. Okay, a little bit of a nomenclature exercise for us this morning. Which of these alkyl halides or halides will give sec-butylbenzene in Friedel-Crafts alkylation? Go ahead and talk to your neighbors. All right, let's try to finish this up in the next 20 seconds or so. Get our final answers in. You got it? You got it set? Okay. We got any more answers coming in? Going once. Okay, there's another one. Any more responses out there? 27. Do I see a 28? All right, that looks like as far as we're getting today. All right, we'll cut it off. Oh, which alkyl halide or halides will react to make sec-butylbenzene? Which ones? Yes. Okay, A and B, right? So B will form a secondary carbocation directly. The second sec-butyl means it's a secondary alkyl group. So the carbocation in B will react directly to give sec-butylbenzene. In A, we'll have the same rearrangement that we drew on the board over here to give the same carbocation that gives sec-butylbenzene. What kind of alkyl group do we get from C? We get a tertiary alkyl group, right? So then that one would give a tert-butylbenzene. Okay, very good. So it's important to note that because we're not forming carbocations in a Friedel-Crafts acylation, we're forming an acylium ion, which is different. It's a resonance stabilized cation. There are no rearrangements in Friedel-Crafts acylations. Okay, that's important to note. All right. So the final point we're going to make about Friedel-Crafts reactions is that other functional groups that can form carbocations can be used. It doesn't have to be an alkyl chloride. We can protonate alkenes with sulfuric acid to form carbocations. And we can use those carbocations in Friedel-Crafts reactions. Here's an example of that. Okay, we're forming this cyclohexyl cation, benzene attacks, HSO4 minus deprotonates. So alkenes can be used. We've made carbocations from alcohols before. And here's an example of that. This is one from my own lab that we did several years ago in the lab. Tertiary alcohol, protonate with sulfuric acid, lose water, benzene ring attacks. This also shows us that we can perform intramolecular Friedel-Crafts reactions. If our carbocation and our benzene ring are in the same molecule, when you form the new carbon-carbon bond, you're also forming a new ring. In this case, we formed a 5-membered ring. This was the bond that was formed in that reaction. Okay. You can also perform intramolecular Friedel-Crafts acylations. The book shows an example of that. Our alkyl chloride and our benzene ring are present in the same molecule. We form a 6-membered ring here, and that can be converted into LSD. I wouldn't do that at home if I were you. The first chemist who synthesized LSD went on the world's first acid trip because LSD is so potent, about 1/10 of a milligram, just a teeny tiny speck is going to give you the psychedelic effects. And so it's impossible not to ingest that amount if you're anywhere near it. So he synthesized it. He was trying to make a pharmaceutical. He accidentally went on a mild acid trip. He wondered if it was the LSD that did it. So a couple days later, he tried it intentionally and had a really wild experience. LSD is an interesting molecule because it's a member of a family of compounds called the ergot alkaloids. LSD does not naturally occur in nature, but relatives with this same ring system do, and they're called ergot alkaloids. They come from a fungus called the ergot fungus, and they're poisonous. They can cause all kinds of symptoms, uncontrollable shaking, numbness or tingling in the extremities, pain. There have been lots of cases of ergot poisoning because it can happen to grain. If grain is stored somewhere that is too cool or too moist, then it can become, this fungus can grow. And when you eat that grain, you can get ergot poisoning. And this happened a lot back in the 1600s through the 1800s. Perhaps the most famous one, which is not documented but suspected, is the Salem witch trials. Salem, Massachusetts was built next to a swamp. The summer before the Salem witchcraft episodes was damp, very cool and moist. And it's speculated that their grain got infected with this mold, this fungus, and then that when they ate bread made from this grain, that some of the young women in Salem started suffering the symptoms of ergot poisoning, which overlapped with the symptoms of being bewitched by a witch. Not knowing what it was, they accused elderly women in the community of bewitching them. And initially, it was probably real symptoms that these young women were feeling. But once they realized they had the power to accuse people of witches, then it kind of took on a life of its own. So it's not documented, it's not known that it was ergot poisoning, but it's strongly suspected, and it certainly makes sense. Okay, so LSD, an interesting molecule, not occurring in nature, but related to poisonous molecules in nature. Don't try this reaction at home. So next week, we will discuss electrophilic aromatic substitutions of substituted benzenes. So today we only looked at benzene itself. What happens if we have a substituent already attached to the benzene? Two questions we'll have to answer. Will that molecule be more reactive or less reactive than benzene? And where will the new substituent attach, ortho, meta, or para? So those are the questions we'll answer on Wednesday. Remember, Monday is a holiday. Please be safe. Please don't get COVID or quarantined over the weekend because we want to see you in class on Wednesday.